Okay, so we talked about polling and interrupt last time, but I want to just use the next couple of slides or next sequence of slides to show you again. I particularly like these set of slides because of the animation. I hope you understand better the concept of polling and the interrupt. So suppose a peripheral intermittently receives data, which must be serviced by the processor. So we're talking about two things. We have a processor and we have a peripheral device. Really the peripheral is just the word saying that there's a thing outside the microprocessor or microcontroller you need to talk to. The processor can get the data by using polling. That means it has to use instructions to keep checking the status of the peripheral and check, are you ready, or do you have data? Do you have data? If you do, then we'll go ahead and read. But if you do the polling, you're actually going to spend a lot of CPU cycles on doing that instead of doing something more useful otherwise. That's why we have this concept of interrupt. Peripherals can interrupt the processor when it has data. Now, for this to happen, physically, there has to be an extra pin or pins. At least you need to have an interrupt pin if you want the microcontroller or microprocessor to respond to these external events. If the interrupt pin is 1 or a logic high, the processor will respond by suspending the current program and jump to a ISR, interrupt service routine. So this is known as interrupt-driven I/O. Underneath, how this works is that essentially the polling of the interrupt pin is built into the hardware. So instead of spending instructions to read the status bit of the peripheral, the processor itself has some built-in logic which will sense the voltage level at the interrupt pin. And from this hardware circuit, if it detects there's a pulse on the pin or a high voltage logic high on the interrupt pin, it will start the interruption process. So the processor will suspend the current program, jump to SR, etc. So this polling function is built into the hardware itself. As a result, the processor does not need to use instructions to check the status. There are several ways to find the ISR, especially the entry address of the SR. We call it interrupt address vector. The very basic one is fixed interrupt. You find this more often in low-end microcontrollers where there's only one interrupt. So there's really no need to differentiate what kind of interrupt. So this address is built into the processor and cannot be changed. So the ISR can be stored at that address, or you can put a jump instruction at that address and then jump to another address. But either way, there's only one interrupt, and the address sometimes like 004, 008, and that's the fixed interrupt address. The second type is vector interrupt. A vector interrupt is that you need to provide the actual address where the processor needs to use to find the ISR. So the exact address in the memory. This is common when microprocessors has multiple peripherals connected by a system bus. So you want to tell the microprocessor that, hey, this is for interrupt service routine 1, this is for the other one. You can have a compromise of these two to expand these possibilities. You can use the interrupt address table, and in a table, you can store the address. And for higher end microprocessors, such as Intel, Atom, or Xeon processors, they all use interrupt address tables. Okay, so let's start with this picture. We are seeing here the behavior or the activities on both of these two actors. So we're looking at the time goes from, vertically from top to down. So this is earlier, this is future. And we have two columns. This several boxes on this column shows the behavior of the microprocessor. And this few boxes on the right side, this column shows the behavior, the activities of the peripheral device, which is represented using P1. And we'll proceed from top to down on the time axis. You can see there are several things happening, which will show using animation in the next few slides. But essentially, the microcontroller will execute a few things, and while it's executing its main program, this peripheral may receive data, and the data will be put into its register, and the register has address 8000 in hexadecimal. And because of this receiving this data, P1 will assert this interrupt signal to notify the microprocessor that you have to stop whatever you're doing and to get this data out of this peripheral because it's important. So the microcontroller will say, okay, let me finish the current instruction, which could be at address 100. And the microcontroller sees this interrupt signal. And so this pin is asserted. So it will save the PC, this stands for program counter, saves the current PC's value 100 and set the PC to the ISR, the fixed location of 16. So this fixed location, 16 is just, for this particular microcontroller, it could be a different value. The point is, it is a fixed ISR. So the address to the first instruction of this ISR is fixed at 16. So the microprocessor will proceed to that ISR, which will read data from this address 8000, which is the address of the peripheral, modifies the data based on the program, and writes the result to a different address, 8001. And after that, actually at the same time or around that time, because this data is read, so P1 will deassert the interrupt. And finally, the ISR returns on the microprocessor side, and then it will restore the PC to the next instruction, which is about to execute before the interrupt, and then the microprocessor will resume executing. So this is the overall process. So let's look at these animations to understand better how they actually function. So we have a program memory, and this is the main program. At this point, the microprocessor is executing this main program. So the program counter points to this address 100. So there's an instruction here. And we have also in the program memory a interrupt service routine, which is located at address 16. We say this really mean that the starting address of this SR is at 16. And of course, there are often times we have more than one instructions. So we have 16, 17, 18, 19, and so on, until the last instruction, which is return from ISR, so RETI. And this is the microprocessor we are trying to follow here. On the other side, we have a few things. We have a system bus, and the system bus has address and data, address bus and data bus, plus some control signals. And on the system bus, we connect data memory. We also connect some peripheral devices, which we indicate here as P1 and P2. Each of them has their own address. P1's address is 8000, and P2's address is 8001. And inside these peripheral devices, there are certain resources. In our case, we only have one register in each of these two peripheral devices. So when you read from 8000, you're actually reading the value of this register. And for the case when you write to this 8001, you're actually putting data into this peripheral 2 here. So the first time, the first step, the microprocessor is executing its main program. So it's somewhere here. And P1 receives input data in the register with address 8000 in hexadecimal. So really, this is what happens here. The data goes into this register. Now, we're not really showing you how exactly this happens, but based on the design of the peripheral, it interacts with certain physical system. So there will be some information coming in, and we say this is the data that we store in this 8000 address. This is the new data. The second step, P1 is going to assert this INT to request servicing by the processor. So you see here, this is a physical wire that connects the microprocessor with the peripheral device. When this goes to 1, this indicates that P1 has data. So the microprocessor will complete whatever instruction is currently executing, which is 100. And it sees INT is asserted. So it has to save the value of 100 and sets the PC to the ISR, which is at fixed location of 16. So in this way, the microprocessor is going to execute the first instruction in ISR. And that's what's happened here. The ISR will be executed. So it will read data from this address. And we're using memory mapped IO. So you can essentially use a move instruction to read data from this 8000 and put it into this internal register R0. And there could be some other instructions following to modify the value of this register. And if we're satisfied, we'll then output this data to this peripheral P2. So we move R0 to this address here to write this new value to the second peripheral. And then this interrupt service routine returns. And while at this 16, because this is a read instruction, this will read data from P1. When you read, you actually assert the signal. So there will be read signal asserted. So P1 itself knows how, when this microprocessor read the data. So it will then deassert this INT. So this 1 will be deasserted. And also, when we write this data to another address, so this new modified data in internal register R0 will be written to this peripheral P2. This is what we just mentioned. The interrupt signal will be deasserted. And the last step for the microprocessor will be to resume the main program. So it will restore PC to 100 plus 1 because it knows 100 was the last instruction it finished. So it will be executing the next instruction at address 101. All right, so the next few slides are very similar. It captures the process of the interrupt. We have the microprocessor doing a few things and also the peripheral doing a few things. However, the difference between this case and the previous case is that in the previous case, we use a fixed interrupt. So 16 was the only number possible, and the peripheral doesn't need to provide such a value to the microprocessor. In this case, we are using vectored interrupt. Vectored interrupt, you can see the major difference is in step 4, where P1 not only will assert the interrupt signal, it will put a interrupt address vector on the data bus. And the 16 could be other values. And the peripheral has to put such an address on the data bus to tell the microprocessor where is the ISR. Okay, so let me again show this. We've seen this. We have the microprocessor here. We have peripheral devices on the other side. We have our program memory with main program and interrupt service routine. And we have the program counter. The buses are the same, although we have one more pins related to interrupt. We had interrupt signal, and also we have an interrupt acknowledgement signal. Interrupt acknowledgement signal comes from the microprocessor to the peripheral. So you see this arrow direction here. And we'll soon see how interrupt acknowledgement pin is put into play. So again, we have the data arriving. So peripheral 1 will be raising the interrupt. And while microprocessor finishing the last instruction, it sees the interrupt signal is asserted. It will save the value of the PC, and it will assert interrupt acknowledgement. So this is a feedback coming from the microprocessor to the peripheral who generates the interrupt. This is to tell the peripheral that, okay, I'm ready to accepting your interrupt vector. So tell me where I should go to find my interrupt service routine. And then this peripheral detects the interrupt acknowledgement. So it knows the microprocessor is waiting for it to tell him or her the address of the ISR. And it has this address 16 in mind, so that's the number it will put onto the system bus. Microprocessor will read this value from the system bus. This value cannot go on these two wires because there's no way you can transfer value 16 using these two wires. So this is actually a value that will go through the system bus, through the data bus. It goes into the microprocessor. And of course, this 16 is not a universal value here. Depending on the microprocessor, you may have other different values, 20, 32. So this is just an example here. And the next thing is the same as in the fixed interrupt case. So ISR will be executed. We have this data processing, and the updated data will be put into a different peripheral. And finally, microprocessor will return to the main program. Okay, so that was the very interesting animation that I think will help you to understand the how the interrupt works. Also, beyond the fixed interrupt and vectored interrupt, we have a third kind, which is using the interrupt address table. It's a compromise between fixed and vectored interrupt. We still use one interrupt pin, and the table in the memory will hold an SR address. The peripheral does not provide an address, but will use an index that into the table. So let's say the table has 256 words. Each word is an address that the microprocessor can use to find ISR. The peripheral will just say, okay, you go to find index 0, find that address in the table, and go to that ISR. Or go to interrupt 15 and use the address in that location of the table, and then that's the entry point of the ISR. So in this way, you can use fewer bits to specify the interrupt number, and also you can move the ISR location